We have next speaker, Professor Davide Dardari from University of Bologna, Italy. He is going to talk about self-conjugating metasurfaces for communication sensing. So he always comes up with new ideas and new sort of concepts. I really like that thing about his research. So hopefully we'll learn something new, because I see that you do work on some metaprism and some smart.
So this is another.
That's what I was thinking about. Next time. So let's see how it works, the metasurfaces for comms and sensing, and over to you, Davide. Thank you so much. Yeah, I will
So this work has been done in collaboration with Marina Lotti, Nicola De Cardi, and Gianni Pasolini. I'm from the University of Bologna, Department of Guglielmo Marconi. This activity was funded by the European project, TG Shine, and the Italian project. Well, so we already discussed today of new applications, in particular massive digital twins, and in particular what regard the applications in industrial environments. You know that there are a lot of very stringent requirements for next generation wireless networks. In particular, we need sensors and devices with extremely low complexity and energy consumption. We just talked about energy consumption. And the transmission of very short packets, so that we need extremely low overhead during the transmission. Very short beamforming access in case we use multiple antennas, grand freedom random access, so that uncoordinated access to the radio spectrum. In some cases, sensor might be attached to rotating parts of the machines, so that in this case we have extremely fast variations of the channel. And at the end, also localization and sensing capability at the centimeter level. So all these requirements are very, very difficult, very challenging to be met at the same time. So we have also some technology drivers for CG, that's listed two. One is the exploitation of higher frequency bands, so millimeter wave and beyond, so up to terahertz bands, so that we gain more bandwidth, so higher speed, lower latency, at the same time positional resolution. Also, reconfigure intelligent services. So we had some talk today on that. Represent a good solution, especially if you want to extend the coverage at low cost and low energy consumption. But also they can be used to perform some signal processing at the electromagnetic levels, as we've seen this morning in the Marco Lorenzo talk. So today, what I would like to put the emphasis is what are the main changes in order to meet the requirements I listed before when we want to exploit the high frequency bands, so millimeter waves and terahertz bands. So we all know that if you have a single antenna link in free space, if you increase the frequency, the packet loss increases with the square of the frequency. Okay, so that the common let's say feeling that is not a good idea to increase the frequency from the packet loss point of view. Okay, but you also know that if we have not a single antenna system, but we have a multiple antennas, so we have an antenna array, both the base station access point and the sensor, so that if we increase the frequency and we keep the size of the arrays, so that let's say dimension array fixed, then the packet loss decreases with the inverse of the square of the frequency. So that if we are able to let's say perform a minor communication, it is better to work at higher frequency from this perspective. But nothing is for free. This is true only if we have a perfect beamforming. So the problem is how to guarantee, say, perfect or good beamforming, satisfy the requirement I showed you before, especially in extremely short time with almost no, let's say, overhead. Well, so today, what we need to do if we want to establish a minor communication, so we have a multiple antenna, both the sensor and the base station, we need to estimate the channel, transmit some signaling between the base station and the sensor. The sensor has to perform some beamformings with, for instance, phased array, so on and so forth. So from the sensor point of view, this might not be cheap in terms of energy consumption, complexity, and so on. And also the signaling, the presence of the signaling might prevent the transmission of extremely short packets, especially in random, let's say, grant-free random access manner. Okay. No, we know that, moreover, there is also the time aspect, so the latency aspect. So if we want to establish, for instance, in free space, a minor communication, so ideally, what we have to do is to search what is the best beamforming at the base station, the best beamforming at the sensor. So that takes time. Okay, so there are techniques that can reduce this time, but so if you want to transmit, 32 bytes packets, so there is it is too much. Okay, so that the objective of this talk is to show a potential solution to establish a minimum communication, so from the sensor to the base station, using an extremely simple sensor. So to avoid the CSI estimation, signaling, beamforming, so that to simplify as much as possible the sensor, but still have a beamforming between the sensor and the base station. Okay. And the solution I'd like to explain here is the modulating self-conjugating metasurfaces, SCM, to be adopted at the sensor side. And as I'm going to show you, we can avoid the RF DAC chain. We can avoid the signal processing at the sensor side, so that the sensor is as a low complexity, low energy consumption, don't have any digital bottleneck in this at the sensor side. But obviously, this is not enough. In order to ensure a communication, a minor communication in this case, what we need is a joint communication beamforming scheme that had to be implemented at the base station or the access point, and that I'm going to show you. And as a potential application of this scheme, I will show you two examples. One is the application to minor grant-free random access, one to localization of and sensing. Well, so what is a self-conjugating cell? So suppose that we have an antenna array with M antennas, and suppose that each antenna is loaded with a particular kind of load, which is capable of performing the conjugation, so that the signal reflected by each, let's say, element is the complex conjugate of the incoming signal. Okay, so suppose that we have, for instance, an impinging plane wave coming from a given angle phi, and then in the Zm here is the complex envelope received by the M cell, and the theta m is the phase shift with respect to the first cell due to the impinging angle. Okay, so what we get the output is a reflected signal, which has the same envelope, but with the phase conjugation. Okay, and possibly again, in case there is also some amplification, but in case of passive structure, the gain obviously is less than 1. Well, what is the final result in this case? Suppose that we have a plane wave. The final result is that we have a reflected plane wave exactly the same angle. Okay, so we without any, let's say, processing the cell, so basically the sensor, basically, the reflected signal is toward back to the base station. Okay, so this is a well-known rate of directivity property that has been exploited in past years, especially in antenna theory works. And then there are different ways to implement this kind of technology, for instance, using heterodynamic-based self-conjugating cells, which we have a receiving antenna, and then we have the multiplication by a carrier twice the frequency of the carrier of the impedance signal, so that the output we have a reflected signal which is conjugated. We might implement this using a completely passive device, which is a Vanata antenna, which was invented in the 1960s, so very, very old idea, in which through a proper arrangement of the transmission line for connecting the array, we obtain basically the same result as before, but with a passive device. And more recently, people studied metasurface-based direct-to-direct arrays that are passive. But we can do more because we want to transmit data. Okay, so the idea is to add to the communicating blocks the also phase shifter. So in particular, we have a phase shift which is common to all the cells in such a way to prevent the rate of directivity effect. But the phase shift depends on data. Okay, so like in the sort of the scattered communication, but in which we have also the rate of directivity effect. Okay, so that we can embed data into the reflected signal. And then from the modeling point of view, we can model the reflected vector at time k, so R is the reflected vector, is equal to the impinging vector Z conjugated, because we have the conjugation, and with a common phase shifter, Pk, and possibly a gain. Okay, so that also, this could be the sensor, actually. Okay, so the sensor is very, very simple. We don't have phase shifter, so I mean, we don't have the complicated, let's say, beamforming schemes and so on. The beamforming is automatic, okay, from this. So, so that is very, very simple. So there's no signal processing, basically, no RF chain in the sensor side. But again, this is not sufficient because in order to exploit this property, this model, we need to do something at the base station. Okay, and what I'm going to show you is an example of a scheme exploiting this modulated SCM in order to realize an ultra-fast joint beamforming and communication scheme. Well, so let's take now, so on the right, we have the self-conjugating metasurface I explained before, and on the left, we have a conventional, let's say, access point of base station with a conventional ground antenna array with n elements, whereas the sensor has n cells. And then, so this is a minor channel, so H is the channel matrix, and HT is the Pesquetter channel, which is the transpose of the first one, assuming the reciprocity, obviously. And the main assumption we make here is that the base station is full duplex, okay? Or we can approximate the sort of full duplex communication. Well, so let me show you briefly, because the scheme is quite simple, how it is possible to perform a joint beamforming communication without any, let's say, dedicated signaling, without channel estimation in a very, very, very short time. So let's start from time equal to 0. So the base station generates a guess beamforming vector x0. So x0 is the vector which is transmitted at time 0. Pt is the transmitted power. Okay, that's the guess vector. Okay, so what we receive is the vector Zk at the sensor side, which is obviously multiplied by the channel matrix. We might have some noise because the sensor might have noise as well, especially if the sensor is amplified. Then this is the reflected signal, which is the conjugation of the receiver signal and a phase shift. So what we receive is the transmitted recording vector S, which is conjugated, multiplied by the matrix A, which basically is H H, this is not H transpose, what we would expect, but the conjugate transport, because of the conjugation of the sense. This is the fundamental aspect. Here we have just a transpose without the conjugation, then what I'm going to tell you later will not work. Okay, so that the conjugation is fundamental for this. Then we have also the noise of the coming from the terminal of the receiver, but possibly also environmental cluster. Okay. Okay, so with the receiver signal, which is a vector, obviously, the base station estimates, generate an estimate of the next recording vector. So this is what will be transmitted the next time instant, which is the conjugation and normalization version of what has been received. Okay. So this scheme is a modified version of the well-known iterative power method, which is a iterative method to estimate the top eigenvector of a square matrix. Okay, so this is just an application modification of this. Moreover, as I'm going to show in the next slide, it is possible to retrieve by correlating the past recording vector and the current recording vector a decision variable in order to estimate the data transmitted by the sensor. Okay, so this is a very simple scheme. So this is an iterative scheme, and what is the result of this? So suppose that for a while you don't have the noise, no noise. So the absence of the noise, basically this is nothing else apart from the presence of the data, nothing else than well-known iterative power method. So we are sure that for large scale, the precoding vector, so after some iteration, the precoding vector will converge to the top eigenvector of this matrix. But the top eigenvector of this matrix is proportional to the left eigenvector of the channel matrix. So that and the left eigenvector of the channel matrix is the optimum beforming, okay, vector. Thanks to the conjugation operated by the sensor. Moreover, the conversion is toward this top eigenvector multiplied by this accumulated phase shift. So if we correlate xk with sk minus 1 conjugated, then we can extract the last phase shift, and then from this we can decode also the data. So we can at the same time decode data and converge to the top eigenvector. So basically we obtain so this picture is corrupted. I don't know why. Anyway, there was some beams. Okay, so we have a perfect beam forming at both sides. Okay, even the presence of mounted parts and so on and so forth. Okay, but this is without noise. The problem is that at each iteration we have a new sample of the noise the next loop, both at the base station and the SCM case. Okay. So the problem is, the question is, does this scheme still converge on V1 or not? Well, it depends. So we performed a study, and we came out with an iterative formula which gives us each time instant, which is the signal-to-noise ratio we obtain starting from the previous one. Okay, so if we apply iterative this formula, we can study the behavior time by time of this signal-to-noise ratio, where key parameters given by this SNR max, where SNR max is defined as the maximum signal-to-noise ratio we would obtain in case we, let's say, concentrate all the power to the to V1, to the, let's say, optimum top eigenvector. Okay, so basically it is the theoretical maximum signal-to-noise ratio we can achieve with perfect uniform. Okay, so it depends on this parameter. Well, but what about the convergence properties of this formula? So if you study the convergence properties of this formula, you discover that starting from a guess initial beamforming value for the vector for x0, so suppose that we don't have any a priori information about where the sensor is, for instance. If this quantity is called SNR bootstrap is larger than 1, then after after a few iterations, the synchronous ratio is converges to the optimum one. Okay, independently on the initial guess number. Instead, if this SNR bootstrap is less than 1, then we have still a convergence, but to the noise, so that we can establish a communication. Okay, and where the bootstrap SNR is defined as the optimal SNR divided by n. N is the number of antenna base station. Okay, so let's see an example, numerical example. So here we see on the left the evolution of synchronous ratio for two different, let's say, guess initial values as a function of the time. So the blue and green curve refer to this situation, which the SNR is larger than 1. And then we see that after a few iterations, so 5, 6 iterations, we have a convergence. The convergence. The convergence is independent of the initial guess. Okay, the final convergence. Whereas in this case, the red one is the case where this condition not satisfied, and then we have the conversion to the noise. Fortunately, even so, this is in case of rank 1 channel, so for instance, free space. But that works also in the presence of a more complicated channel, for instance, multiple channel, which we have in this case a rank 3 channel. And see here we see the evolution of the so basically, this is the SNR referred to the first eigenvector, and these are SNR referred to the second and the third eigenvector. So we see that after a few iterations, we basically converge to the first eigenvector, and all the others vanishes. Okay, so the key takeaway message is that the conversion doesn't depend on the initial random guess. So this is good because we don't need any a priori information to get the convergence. The bootstrap SNR, which is a key parameter for the convergence, increases with n, the array size of the base station, and the square of n, the number of servers SCM, so that we can increase this let's say threshold by playing with this number. And at the convergence, we have what we reach is the optimum beamforming at both sides automatically. Okay. Single layer, obviously, because we are just one data stream, so that we adopt the optimal link, optimal communication of my model, okay, for free, basically. So this is a graphical example of the antenna, so the radiation diagram corresponds to the precoding vector X. So this is the time instant k equal to 0, which we have a random precoding vector, so we have a random radiation pattern, okay. After one only iteration, this is the beam we obtain. So it's already quite good shape with some noise, and after 2 iterations, you see that we have the even better, let's say, info. So very few iterations we get the optimum, let's say, beamforming at both sides. Okay. Well, so let me show a numerical example related to a communication to 20 gigahertz, and these are the dimensions of the antenna array at the base station, and the antenna array, the SCM, the sensor, so 5x5 sensor. And here we see the comparison between simulations and theoretical formulas showed you before. And here we see that in this example, so the curves refer to 2 different values for the transmitted power. So for the first value, we have the convergence to the top value after only 70 microseconds. Okay. So a few time instant, whereas if we lower the transmitted power, basically we have the conversion to the noise. There is no. This is static channel. So this is the same result for a dynamic channel with multipaths, And here we tested different velocity, different speeds up to 300 km per hour. And here we see that in general, this technique can track the evolution of actual signal-to-noise ratio. Okay, it may happen that due to the fading, the actual signal-to-noise ratio goes below the threshold SNR bootstrap. In that case, we lose tracking. But as long as the signal-to-noise ratio go above 1, then we have a very fast recovery on the tracking. Let's keep in mind that all this tracking of the beam, so that there is a dynamic tracking in the beam, takes place while communicating. Okay, so there is in background also the communication. So we have a joint communication being formed. So let me show an application of this basic scheme, which is considered just one sensor and one access point, one base station, to implement a grand-free random access scheme. Okay. So now we have many sensors. So this, for instance, the scenario we are investigating the CG Shine European project, which we have several sensors that transmit very short packets randomly, so without any coordination. Okay. So the problem is how to guarantee the grand-free random access with short packets, so with low overhead, by using memory. So that we have an array both of the sensor and the access point. So that's the problem. So we want to ensure that the beamforming is accomplished before the end of the packet. Okay. And so the idea is the following. So this is what is implemented in the base station, the access point. Okay, and here we have a certain number of active sensors, each with a different MIMO channel, obviously. And the idea is the following. So in the access point, we have a scouting task, which is run continuously. Okay, and the purpose of the scouting task is to search for new packets. Okay, search for the new sensor just that wake up. And the scouting task basically implements the previous scheme. Okay, so starting from guess recording vector, and as long as it detects a new packet, it's put the estimated recording vector into database and create, let's say, associate this recording vector with a communication task. We start running in parallel using that particular estimated recording vector. One task is to retrieve the information, to decode the packet until the end of the packet. So at the end of the packet, the communication task will remove the recording vector from the shared database, and the communication task will be, say, ended. Okay, but in parallel, the scouting task continues searching for new packets, and the search is performed in the subspace, the channel subspace orthogonal to that spanned by the current active sensor. How to do that? Basically, the scouting task is performed in the channel subspace, which is orthogonal to all the recording vector put in the database. Okay, so these are all the recording vectors that refer to currently active, say, sensors. So that you keep, let's say, the searching for new packets orthogonal to the current communications. Okay, so there is no interference between these tasks. And so this is an example, a numerical example, in which we compare in terms of mean budget advantage this scheme with a baseline grand-free random access scheme. And as a baseline, we have chosen a CMO active, that means we have an active transmitter, it's not a scattered transmitter, sensors. CMO, because using CMO, we have a fair comparison in terms of complexity. So we have more or less the same complexity on the sensor side. Okay. So that here we see the trade-off between the distance and the carrier frequency for different parameters of the system. For instance, suppose that we fix the distance of 10 meters, and then here we see 50 gigas, more or less. What is the meaning of this? The meaning is that below 50 gigas, it is more convenient, the baseline system, active system, whereas above 50 gigas, the proposed backscatter-based system is more convenient. So it's more convenient for high frequency. So if you want to increase the frequency, according to the discussion I made in the first slide, it is more convenient, this backscatter scheme, than an active one. Why this? Because thanks to the MIMO gain, the two-way path loss we have with the backscatter communication is compensated by the MIMO. Okay. Well, so okay, this is just another example in terms of packet error rate. So for 100 gigahertz transmission, we have also an advantage in terms of packet error rate, in which here we put on top of both schemes a norm in order to compensate for possible intersection interference, because it may happen that the MIMO channels referring to different sensors are not orthogonal. Okay, they become orthogonal if we go massive MIMO, but in non-massive MIMO condition, obviously depending on the position of the sensor channel cannot be completely orthogonal, so that we might have some intersection interference, and it can be mitigated by using a normal, for instance. And the last example is use the same method to realize real-time localization. Here we can foresee two different architectures, so basically complementary architectures. The first architecture we have this classical, say, position architecture, which we have a bunch of anchor nodes located in known position, and then we have one or more user equipments that move in the area, and we want to localize, so the system wants to localize the users. And suppose that conditional that the users are equipped with the LTM, so they are almost scattering devices, so very, very simple devices. So here, the purpose in the first architecture is to have a low cost of energy UEs, whereas in the second architecture, we have the reverse. So basically, the anchor nodes are made of SEM, so they are very, very simple devices. This is a typical navigation scenario, in which the UV could be a more complicated device. For instance, a forklift moving inside a factory, in which the anchor nodes are very simple labels put in the environment, and then here the purpose to again to localize the user equipment. In this case, it's the user equipment that localizes itself based on the interaction with the anchor nodes. Well, so not to save time, not go too much in the details. So the idea is to have the SCM-based node scattering continuously an ID, for instance, a pseudo-noise sequence, which is different from each SCM-based node, so that the active node implements the scheme I explained before, so it can discover the different SCM nodes, so that it can estimate the best frequency vector they pointing towards each SCM nodes, and starting from the frequency vector, if you are in a line of sight condition, we can estimate the angle of arrival. So by making just an FFT operation on the precoding vector, we can estimate the angle of arrival, so that by means of triangulation, we can estimate the position of the node. So this is the basic technique. Okay, this is again that we show some numerical example. This is a 28 gigahertz example, in which we have 4 anchor nodes with the 2 users moving inside the area. And this is an example of empirical CDF of the absolute localization error for the first architecture. So for different conditions, don't have time now to explain different conditions, but just to show you that it is possible to obtain a centimeter level accuracies using extremely simple let's say, the scattering devices. This is more or less the same for as a function of the size of the SCM device. So if we obviously increase the size of the SCM device, we can improve the accuracy. And this is the same result for the second architecture. So in blue, you see similar performance as before, so for the second architecture. The other curves refer to the case where we have some orientation error, and then obviously orientation error might compromise a little bit the performance. So summarizing, it is possible to exploit the SCM also for positioning, so that we can obtain a very simple, cost-effective, energy-efficient positioning system without dedicated signaling and without any onboard signal processing capability. And this also reduces the localization update rate with respect to, let's say, current systems. Okay, so in conclusion, basically, the adoption of modulating self-conjugating metasurface may offer some advantages, especially if you want to establish an ultra-fast beamforming in a manual configuration without channel state information estimation, and with extremely simple sensors that don't require RF chain, signal processing, signaling, and so on and so forth. And then it is possible to establish this manual communication in just a few iterations, and this can be applied to grant-free amount of access, localization, and I think that this let's say, technology can be appealing, especially for industrial IoT applications where we have the issues I mentioned before. So that's all. Thank you for your attention.